The following program is brought to you by Caltech.
Good evening. My name is Tom Sofer. I'm the chairman of the Division of Physics, Math, and Astronomy, and one of the best parts of my job is being able to introduce speakers who tell you about some of the exciting work that's being done in our division. Before I do that, I need to take care of a little bit of business. First thing is to tell you about the next lecture in this series, the Watson Lectures. Next lecture, which is the last of this academic season, will be given by Beverly McCoon, who will speak on May 16th. Her topic will be Taming Turbulence. The other thing that I want to tell you is that tonight's a historic night. This is the first time that a Watson lecture is being streamed live. It's being streamed live to a meeting of the Caltech Associates in the Bay Area. So I want to, those of you who are attending that event, welcome to this historic event. So now it's my real pleasure to introduce tonight's speaker, Sri Kulkarni, who is Caltech's John D. and Catherine T. MacArthur Professor of Astronomy and Planetary Science, and he's also the director of the Caltech Optical Observatories. Sri received his undergraduate degree in physics from the Indian Institute of Technology and his PhD in radio astronomy from the University of California, Berkeley. He came to Caltech as a Millikan Fellow in 1985, and we've been lucky to have him as a member of the faculty here ever since. Sri is a singular person, even for Caltech. His discoveries are many, and his influence on astronomy is enormous. He discovered the first millisecond pulsar, the first brown dwarf. He led the team that discovered soft gamma ray repeaters and the team that placed gamma ray bursts at cosmological distances. I could spend the next hour telling you about his many honors and awards, but I'll just name a few. He received the Warner Prize of the American Astronomical Society and the Alan T. Waterman Award of the National Science Foundation. He's a fellow of the Royal Society of London, a member of the National Academy of Sciences. Most recently, he was named an honorary fellow of the Indian Academy of Sciences. Sri likes to reinvent himself every 5 to 10 years, and he's always inventing new fields, leading the way into new, exciting areas of astrophysics. In his current incarnation, Sri is leading the world in discovering the richness of the transient universe, which he will tell us about in tonight's lecture entitled An Explosion of Explosions. After his talk, he will take questions. So with that, let me introduce Sri Kulkarni.
Good evening. It's a great pleasure to give this talk, mainly because it's very largely based at Caltech facilities and has substantial contribution from young people at Caltech, students and postdocs. The basic talk is really about exploding stars, of which there are many kinds actually. And since I was told I have only an hour, I decided to focus primarily on supernovae, which is a subject which actually began in Pasadena. So we'll go through a bit of the history of this subject, which is intertwined with the history of Caltech, and then we'll end with things that are happening at Palomar. So looking for things that go bump, burp, or boom in the sky is something that happens pretty routinely. There's a very large amateur community in the world. Typically, if you look at the way astronomers communicate with each other, so-called Astronomer's Telegram or IU Circulars, you'll find many amateurs contributing to this. And so what we now call as novae and supernovae, which is a word, for example, supernovae, we no longer hyphenate it, but when it was used here in Pasadena in 1934, it was a hyphenated word, and it's now entered the English lexicon as a proper word. So here's an example of a nova. In this particular case, it's observed by an amateur, and many times they're really discovered by amateurs, and then the astronomers do detailed studies. Nova is actually a short term for nova stella, or a new star. And they've noticed there's a long history of new stars, starting with Chinese observations of what we now call as supernovae, through observations by Korean, Japanese, and even American Indian tribes in Arizona and Central America observed, for example, the Crab supernova. But the subject really became pretty popular about 100 years ago. At that time, perhaps the greatest place in the US leading astronomy was the Harvard College Observatory. Mind you, I'm talking 100 years ago, not today. Okay. And one of their focus was, in fact, to accumulate nightly exposures of different pieces of sky. And in fact, if you go to Harvard, there's a huge collection of plates. And the study of variable stars was something all first-rate astronomers used to do. Okay, but let's understand, where did the word supernova begin? It actually began here at Palomar, and this is an aerial view of Palomar. It's only about 120 miles from here. And while this is a modern view, it shows, of course, the mighty 200-inch, which reigned supreme for nearly 4 decades. And this is the 60-inch student telescope. Here's the 48-inch Ocean Schmidt telescope. The real story began here with the smallest telescope that you see on the mountaintop, which was the 18-inch Schmidt telescope. And this was, in fact, the first major telescope that came on the mountaintop in the early 30s, while work was proceeding on building the Big Eye, the 200-inch telescope. And the pioneering work done by Caltech professor Fritz Zwicky and associate Walter Bade at the Carnegie Institution led to the distinction that what is initially termed as new star to mean anything which came new, that in fact their families began all with this telescope. Perhaps if you ask me who's like the most famous astronomer from Pasadena, I would say it was Fritz Zwicky. He seems to be an amazing person. And perhaps if you don't know that name very well, it's also he was perhaps not very diplomatic in the way he dealt with people. And so maybe others are better known. But he probably was a genius in his contributions, ranging from fundamental patterns in jet engines through astronomy and actually philosophy. Okay, so Zwicky found when Walter Bade, his associate, informed him that a German optician called Schmidt had invented a new corrector camera that could take pictures of the sky through a telescope and its wide angle. So the difference I'm making here is that you can, of course, take wide-angle pictures with lenses that you all use, but this is a combination of a lens and a mirror, and it's still a unique arrangement. And so he immediately realized there's a huge value in exploring the sky with a wide field imager and seeing what things may happen. So in some sense, the systematic study of changes in the sky really began with Zwicky, and here's the Zwicky observing at the 18-inch telescope. So the work he did with Walter Bade quickly led to the idea that what is called as nova, which is a new star, in fact, could immediately be divided into 2 categories. Novae, which are things that happen in our galaxy, and nearby galaxies, because they're intrinsically faint, so we can only see them nearby, and super-nova, which means they're much, much brighter than supernova. And more or less the history of, as I said, the history of supernova began in Pasadena. This telescope was incidentally supported by his wife's family, which is a well-known Pasadena family called the Gates family. The 18-inch was so successful that Zwicky was able to persuade Caltech administration that they should build a larger telescope, Schmidt-type telescope, 48-inch, so that it can survey the sky and undertake systematic studies and find new things which could then be fed to the 200-inch for further detailed studies. So both of these telescopes more or less came online, and amazingly enough, both of telescopes, despite the difference in their sizes, have contributed about as much equally to the astronomical literature. Okay, so let's focus now on only one part of the new star family, the supernova. And I don't want to leave you with the idea that supernovae is just one family. As it turns out, the work done since then and the work we have done with the project I'm describing today, the Palomar Transient Factory, we now know there are many families within supernovae. There's an amazing richness of stellar explosions. But roughly speaking, every time a star dies, a supernova is born. Stars which are not very massive, like our sun, they don't have a spectacular ending. They, like most of us, they kind of get fat, and then slowly, they actually then become what are called as degenerate stars. And it's not what you're thinking. It's an astronomer term to just mean a star which is supported by degeneracy pressure with no bearing on its moral turpitude. Okay, so here's Messier 51. It's a favorite for amateur astronomers. It's a beautiful galaxy. If you have a small telescopes, it's one of the nice things to see. And you can see that this is virtually a factory. It's a veritable factory of supernovae. Here's a supernovae in 2005, another one in 2011. And these come from the deaths of massive stars, which is how story in some sense begins. But we now know there are other sorts of deaths. There are stars which are reborn and re-die and so on and so forth, and you will come to it as we go along. So you might say, you know, many times I'm always asked as an astronomer, well, what's it to me, you know, that you guys study the skies? It doesn't make much difference to things on Earth. Well, yeah, yes and no. Should an asteroid strike you, well, it'll certainly make a huge difference to your life. And then you'd say, how could I get my nearest astronomer? But let's not wait for such catastrophic things to appreciate astronomy. I would say the reason you study the sky is because that's what people who are thinking want to know, where they came from, how the universe works. It's a very simple curiosity. And if you don't have that, I don't know what else we have, actually. So let me tell you why supernovae are interesting. If a star did not die, you wouldn't be here. So you should be very, very thankful stars are dying. There's a supernova every second. Supernova, supernova, supernova. Not in our galaxy, thankfully, but somewhere in the universe. And you say, well, so what? If a star dies, why it's of interest to me is because when a star dies, then new elements are created. We are now pretty sure, well, quite sure, that the universe began in a rather simple fashion. The universe was rather boring when it began. It has hydrogen, helium, and a bit of lithium. And I said, thank God, you know, at least for some of my colleagues, we had some lithium there. Okay. Well, anyway, okay. So, and that's it. And the universe was very uniform, very homogeneous. The difference between the density of matter and photons over there to over here was only a part in a million. It took enormous effort, technical effort, on part of astronomers, including pioneering work done here by Professor Lang and Professor Reedhead, which was able to see these differences, okay? Well, the universe became complex in two ways. First of all, it's not homogeneous right now. If you look around, we have galaxies, and the huge volume of which is between galaxies is empty, okay? So some of these little perturbations or little excess densities became these very condensed things. But so if you just had hydrogen, helium, big balls, well, you know, you wouldn't be here. There's very little helium in us, and a little bit of hydrogen, but really we are made of other things. So when a supernova dies is when the periodic table starts becoming interesting. So I really want all my chemist colleagues to appreciate, without astronomy, you won't be here at all. So we start with hydrogen, helium, primarily 90%, 10%, and when a star starts dying, immense nuclear reactions take place. As you know, even the sun is basically being powered by nuclear reactions. It's only making hydrogen to helium. But when they're dying, they start producing carbon, nitrogen, oxygen. If it's more massive, then you get oxygen, silicon, magnesium. And in some cases, if you know mass, you can go to iron. And if a neutron star is formed, you can get so-called very neutron-rich elements, and you just go down the periodic table. Okay, so so much so that astronomers, and I know it will certainly shock anyone here in the audience, that we call anything other than hydrogen, helium, and lithium as metals. Because that is sort of the new stuff that came along, okay? It's not, I know it's not metals by ordinary standards. Okay, so I've given you some sort of a background of what supernovae are all about. And so part of astronomy, to me, astronomy is a phenomenological study. It's like biology. There is no absolute theory of astronomy in my mind. There is no one who can say, starting from basic physics of equation, I predict the universe will be this. Well, if there is someone, please introduce me, introduce yourself to me, because I have not met anyone. Same way, there's nothing in biology, which is what I call as theoretical biology. No one can say why a rabbit should be a rabbit or a wolf should look like a wolf, okay? So the job of these sorts of fields is to go and discover new beasts, is to go and hunt them. I don't mean with rifles or something, but to go find some things about them and chart the universe. And somewhere along the line, sometimes you're lucky you find something very interesting. Okay, so instead of saying go and find new and weird stuff, the technical term for that is called exploration of phase space. It's pretty standard, and this concept actually was also introduced by Zwicky in one of his more philosophical moments. So phase space is a simple graphical way to kind of put things together. So for example, you can think of a diagram. On one axis is the mass of a person or the weight of a person. The other axis is the height of a person. And it's actually a sensible phase space, because you'll see that when people are sort of typically very small or low height, they also have low mass. And in fact, there's a progression in this phase space, more mass, more height. And then you'll see some groupings, and that's how this sort of phenomenological studies begin. So here's a phase space for astronomy, and that is on one axis is the absolute luminosity, or which means the brilliance, how much energy is coming per second in very weird units. And the reason we have weird units in astronomy is something perhaps no one has ever told you. Our subject is so interesting. Our biggest worry is that many of our colleagues who kind of work on more boring things would want to do astronomy. So the first thing we would do is we introduce some weird units, and that usually gets the competition away. Okay, so instead of saying absolute luminosity, we call it a V-band magnitude, and the more negative the number is, then the more brighter it is, okay? That's how it is. I just wanted to appreciate that. And the other one is the time scale of the phenomena. How long did it last, okay? So here's novae, they're not as bright, and here's supernovae of a certain kind called 1A, and you can see there's a vast space between them. The whole thing is white. And for an astronomer, the answer is very simple. There's stuff to be found there, or we need to do experiments to explore the phase space. Okay, that's one idea. This is a basic astronomical thing. If you don't understand this, you're not an astronomer, okay? You really want to go and explore phase space, okay? Or you want to go and find new and interesting things, hopefully something which will be really exciting. Okay, now there's but you know, if you write a proposal, it says, yeah, I like to actually, I'm very curious, I'm a scientist, so give me money. Usually the National Science Foundation will turn you down because but so you have to give a bit more articulated reasons which sound more scholarly. And here's a slightly more scholarly view of why this is interesting. And there are new and frontier areas of astronomy and physics. And the relation between astronomy and physics is very interesting. Physics is all about reduction. So you'll find all sorts of things and say, what is the one statement that encapsulates the truth? Okay, and astronomy is anything but reduction, is all about exploration. And therefore, there's a huge, very nice interplay between physics and astronomy, as long as you don't get confused between their goals. So many of the new areas of astronomy are usually led by physicists. They're very good at building things and doing things, but once it starts working, they're not so good at understanding the importance. It's natural, it's very hard to do all sorts of things. So here are some new areas of physics, which are, you know, within this decade will become regular areas of astronomy. And the telescopes that these areas employ are really weird and interesting. So here, for example, are energetic particles. So here's the Pierre Auger Observatory in South America, and it's looking for extremely energetic cosmic rays. By the way, the word cosmic rays was in fact coined here in astronomy, coined here at Caltech by Millikan for these energetic particles come from outer space. These are so energetic that the energy carried by a 10 to the 21 electron volt, that's a natural unit in this game, has as much energy as the fastest cricket ball that's been thrown. And I'm not sort of using cricket or baseball. It turns out the cricket balls are thrown faster than baseball. And I actually computed half mv square. I looked at the things, and it's 10 to the 21 EV. And you say, well, you know, I don't see anyone just like getting knocked off in Pasadena, suddenly like they're walking and they're dead. Well, the reason is that the momentum that matters, the momentum of these particles is very small because they're at almost speed of light. Anyway, they're packed with energy. To think a single proton has this sort of energy is mind-boggling. Okay, and the way astronomers or the physicists working this, they find is that they create basically what's called a Cherenkov radiation. They create secondary particles. And so there's all sorts of products come in the upper atmosphere that are detected at ground level. And here's another weird one, is to look for very high energy neutrinos. I just want you to appreciate this. This is the Eiffel's Tower. That's really tiny. And where are we? And then it says bedrock, okay? This is actually the South Pole. This is the top of the polar ice here. And these physicists have drilled holes using hot water and suspended these wires and photomultiplier tubes to find basically the equivalent of Cherenkov radiation for high energy neutrinos. For these two subjects, it's only the nearby universe that matters. When I say nearby, I'm not talking on scale of from here to San Francisco or something, but I'm talking about astronomers' units, about 100 megaparsecs. And just to clarify, a parsec is 3 light years, so 100 megaparsecs is 100 million parsecs, or 300 million light years. Okay, so here's another frontier area, gravitational waves. What this simulation shows is a black hole, schematically shown here. And it just so happens there's a neutron star next to it. Such combinations are expected to exist. Combinations of 2 neutron stars in close orbit certainly do exist. Because this is being accelerated, because it's only an orbital period of a few minutes in this case, it loses a lot of gravitational energy. And if you lose energy, you must therefore make up for that, and you do that by falling deeper into the potential well or getting closer to your companion. So the neutron star is then shred to pieces by tidal forces from this black hole. Material rains down onto this black hole, and perhaps we would see electromagnetic radiation. And we think this is the origin of something called a short hard burst. However, when this is circling around, I told you it's going to lose energy by gravitational radiation. And one expects, we have such good understanding of general relativity because it's passed all the tests so far we know, that one expects to actually see these gravitational waves come out. And in fact, that is the origin of the LIGO project, yet another great Caltech project, whose aim is in fact to find these small perturbations in space-time that come screaming away to Earth. And just the sensitivity limit of these things, it's such a delicate measurement. It's really a very delicate measurement that you can't, even though there may be stuff happening at the edges of the universe, we can only see stuff close to us. So hopefully I have now convinced you there are 2 reasons to study explosions in the nearby universe. One is pure curiosity. The other one is it's the link to these new areas of physics. So I had the Palomar Transient factory got only one goal. Its transients are us. That's all we do. In other words, we want to systematically explore the changing sky. Okay, so here's an observatory which is 50 years old now. The first light was approximately 1950. And so you'd think, well, there are all these new telescopes. There's the Keck telescope. People are talking about the 30-meter telescope. There's JWST. How can something so old compete? So part of the way I like to think is I sort of by nature contrarian. If 10 of you say something, even if I liked it, I'll have to say no. So I was, for a while, a few years ago, I'd taken a mini sabbatical to Santa Barbara. And I was mentioning to a friend of mine, Professor Lars Bilston, that I had this idea that the way to go about doing this was, in fact, to be very focused. So the idea is to use this telescope, which is got this wide field to go and image the sky. Okay, so in a night I can count thousands of square degrees, find something interesting, and then immediately ask this telescope to go characterize it. And then if it looks still more interesting, then use this telescope. This idea of chaining telescopes well, sounds pretty obvious, but wasn't obvious, wasn't routinely practiced in those days. And Caltech has this facility, so we could, so the idea of the factory was have something which is reliable, so we can discover supernovae, exotic phenomena, in a guaranteed fashion, get the production going, and things will happen. And Lars said, well, I said, you know, I have this idea, I don't know how to go about it. He said, well, so sitting in Santa Barbara, there's a little cafe. He said, well, I want you to talk to a friend of mine, you know, it'll be interesting. So I spent some time on the little cafe there. And I met this gentleman who I'm told is a Google mastermind. I didn't know that then. And I explained this idea. And then Wayne Rosing, who he is in the audience today, I'm very happy he came along. Next day he asked me, well, how much do you think it'll cost? I said, well, it'll cost $1 million. Maybe two, and he was very kind to help me out at that point. Okay, so we went from I went from concept to first light in 26 months. I have a background in engineering physics, so I sort of like to, you know, mainly I want to get things done. I don't have time for a lot of very long-term development at all. So I'm very happy that in 26 months, thanks to the effort of engineers at Caltech Optical Observatories, the crew at Palomar Mountain, and of course, wonderful students and postdocs at Caltech, and my collaborators elsewhere, we were able to actually go from this idea to being first on the sky. Okay, so here's some hardware. This is the old CFH12K camera. Here's a mosaic of CCDs, and this is real data. One of the CCDs did not work, and there's a little worry. If you make an image of sky, there'll be a missing tooth. I said, who cares? More area, we'll go discover things. And once we make discoveries, maybe we'll go and fix it. You know, I've never been for elegance at all. And here's the moon photoshopped in. We don't observe the moon. It'll be too bright. It would have washed out all these things, just to give you an idea. And so you need software, and you need hardware. And you actually need something which astronomers are only slowly appreciating, because when you think of telescopes and so on, you always think of giant and capital investment. But a project like this, it turns out the cost of hardware is, in fact, the smallest part of the cost. You need grayware. You need actually smart people. So I went around the world and assembled all these very interesting young people and said, come and work with me. I'll make you rich and famous. And then after a minute, I told them, you know, I'll make you famous. Okay. So Josh Bloom is now professor at Berkeley. Jason Suarez, he's a pipeline maestro. When I say pipeline, it's not the stuff you've been reading in papers. It's a software pipeline. Peter Nugent is one of the world's greatest experts in a particular kind of pipeline called image differencing. Eran Ofek was a postdoc. He has now returned as a faculty at Weizmann Institute. Richard DeCaney, he's our chief engineer at Caltech Optical Observatories. Robert Quimby, he led the software integration team. He's now in Japan. And Nick Law, he's moved on to University of Toronto. He was the project scientist. And all these guys, many of them were just finished their PhD. So I said, I have a very simple management philosophy. We can debate, discuss, argue, whatever, and then we discuss on a schedule and money, how much is needed, and then I don't want to talk to them till 12 months from now, and that's it. Things get done. And here's all these young people that we assemble to help us out. Project like this is really largely software. It is software, software, and more software. There's a very large amount of pipelines because those telescopes that I described, they're all run robotically. There is no one. The telescope is, as we speak, observing right now. The 48-inch doing some survey of the sky. And like Eran Ofek wrote this software that the telescope automatically sequences itself observing. It's not as easy as you think because sometimes there's rain, sometimes there's an instrument failure. It has to recover, get back to its supposed cadence. And then when things are found, the software has to trigger the 60-inch and say, wow, this is interesting to observe. So there's really no one attending to it. So there's a large amount of software. I don't propose to go into this. But the basic process we do is we take a new image, let's say tonight, we compare that to an old image taken maybe a year ago, a month ago, as depending on the experiment. We subtract the two. It is not as simple as A minus B or what you're thinking. There's a lot of nuances because these are not perfect instruments. And that then if you find something here, well, it turns out there's a little bit something hidden there, and that's a supernova. Well, if you do the same thing here, and that's very rare, okay? Sometimes the subtraction is imperfect, and then you know this is not a supernova, because if this is supernova, how about that one? That's because this has not been subtracted correctly. A human can actually figure it out. In about 15 minutes training, you can become a good supernova expert. And in fact, in the beginning, until we had the machine learning algorithms implemented by Josh Bloom and his students at Berkeley, we would actually scan, that is human scanning. We'd look up and say yes, no, yes, no. And then for a while, we had citizen science. I don't know whether you know this. It's sometimes called crowdsourcing. I never heard of that. Basically, crowdsourcing is getting other people to work for you for free, okay? And the way it works is we had something called the Supernova Zoo, following an example of something called the Galaxy Zoo, run by colleagues in Oxford. There's a thing you log in because you want to be a citizen scientist, and you get trained by this software, and then you start doing it. So you come back from a bad day at office, and then you help out the Palomar Transient factory by going through 1,000 of our candidates. And it turns out, I hate to say this, but if you take the average of 10 such responses from the public, it's as good as a professional astronomer. So our signal-to-noise ratio in that sense is only about square root 10 or 3.3. Okay, so all this is done, but now it's all done with machine learning algorithms, which I don't fully understand, but it works, and that's all I'm happy. And then there's a lot of other reduction we have to do, and this is done at IPAC here in the Maurice Rowe building, led by Jason Suarez. There's a huge amount of data. This is just to look at the stars, which are not supernovae. And we're building one of the largest catalogs in astronomy at this point. We'll come back to that. Okay, so what is our net output? Our net output is, as of last night, 1,404 supernovae, which we know what they are. We probably found maybe 3 or 4 times that number, maybe 6,000 likely supernova candidates, okay? But that's not what I'm talking about. I'm talking of things we know. And they come in various flavors. There are different families. The 1A are so-called thermonuclear supernovae. They're very special because it is with the use of these supernovae astronomers were able to demonstrate the first, or suspect the universe, in fact, was accelerating, and the Nobel Prize was given by using these supernovae as cosmic yardsticks. These supernovae are from the deaths of massive stars. They lead to formation of neutron stars. And these are also deaths of massive stars, but there's something slightly special. Of course, the part that's most interesting for an astronomer is 3%, okay? Because each one of them will be a weird thing, and we hope it's more than weird. It's also important. So let's come back to the phase space I described, which is one axis we have how long the event lasts, and the other axis is how bright they are, okay? And this is on a log scale, so don't be misled by, 2 units is not 2 units. 2.5 units here is like factor of 10, okay? This is a huge range in brightness. So we have the classical novae, which are now called as classical novae, and then these thermonuclear supernovae, the so-called 1A. And then we have this type 2 explosions that I showed, which is the next abundant things, which is a massive star dying. The core implodes, neutron star is formed, sometimes maybe a black hole. Well, that's sort of the story that has been around for some time. Well, here's the new thing. We found all these interesting things, and the ones which we have found have a name PTF, ones found by the rest of the world have a name SN. And there are all these new things. So I started off by saying, an astronomer looks at this phase space and says, it's so empty, let's go find these things. Well, there are beasts already. We're finding all sorts of beasts. What sort of beasts do we have? Well, first we have the so-called calcium-rich transients. I don't know what they are, but we know that they're largely, when the star explodes, it mainly produces a lot of calcium. In nuclear physics terms, it's incomplete burning. Because if really the nuclear reactions go all the way to producing iron, iron is actually very abundant, relatively speaking, because it is the most stable element, and therefore nuclear reactions stop there, because if you try to burn iron, meaning fuse iron with iron, you lose energy, and that's why you produce a large amount of iron. Okay, then we have something which I don't know what they are. There are at least 2 families here. We simply call them as luminous red novae, because they're luminous, red because at peak they appear red, to your eye they would be red, and novae because they're new, okay? And there are 2 categories. I won't have I won't go in detail, but the number of luminous red novae we now know of this category, there are fewer of them than the number of ideas of what they could be. And, okay, and that's a good situation to be in, right, for an astronomer, because you're then thinking very imaginatively what else could it be. And then there's a so-called 0.1A explosion. This is something my friend Lars Bilston has done a lot of pioneering work. And we believe these come from the end products of so-called AM Canvan stars, which I'll talk a little bit towards the end of my talk. Basically, these are two white dwarfs which are circling, just like the black hole neutron star example I gave. Your two neutron stars, two white dwarfs circling, and eventually they lose gravitational energy, and then they coalesce, and we believe that this is a plausible explanation. And then there's this whole emerging class of luminous supernovae. Now, compared to the 1A supernovae, which is here, the so-called thermonuclear supernovae, these are 10 times brighter, and they're 10 times more energy loss. Okay, these are already staggeringly bright objects. To think something 10 times brighter and 10 times more energy loss is, I would say, somewhat unexpected. And we now believe that these come from the most massive stars that the universe has produced. Okay, so I'll go a little bit in detail. So the work for this actually began, Robert Quimby, whom I mentioned, for his thesis at Texas using the small telescope. He discovered something called Supernova 2006 GY. Here it is. And here's the light curve. So light curve here means, here's the luminosity in astronomer units versus time scale. 0 is simply given to the peak. That's minus 100 means 100 days before peak. And here's what a 1A supernova would look like. And here's what this particular one Robert discovered looked like. And this started the game. But what PTF was able to do is, in fact, find a whole class of supernovae which are as luminous and as energetic, but without hydrogen. It's a little subtle thing, which I would have no time to explain. It's somewhat easier to understand a luminous supernova with hydrogen, but without hydrogen really requires a rather very interesting channel. And this is what real data looks like. Now, what this shows is a series of spectra. So this is wavelength, and this is in so-called rest frame. That is, if you're in the frame, if you're co-moving with the supernova, then that would be the wavelength. Of course, the supernovae happen at high redshift, relatively speaking, and they are redshifted, but we are corrected for that. And so Robert had found something called 2000 AP, and he had no idea what it was. And with PTF, as you can see, there's various PTF names. He was able to form a sequence, and then he realized that including this weird object, no one had understood that there's a sequence that, in fact, these supernovae are at redshift of a few tenths. Now, we are studying the nearby universe, and suddenly we're going to gigaparsecs. That's how bright these objects are. So we now know that these superluminous supernovae, in fact, are the deaths of the most massive stars, maybe 100 to 300 solar masses. And there's some idea that the early universe would produce such massive stars, though, of course, we discovered nearby. Okay, so I started with a double white dwarf. So nature does produce cases where we actually have two white dwarfs that are in a rather tight orbit. And the technical name is AM Canvan stars. Canis Venetochron, I don't know what it is. It's a constellation, and AM it's just how astronomers name stars. It's a really weird one. So the first variable stars is R Canvan, and then Q, and so on. Then when you reach Z, you start with RR. And then you go back, and then you skip like airplane convention. I think I skipped. Anyway, this is, again, this is a little kind of barriers we have put through this. So this is a variable star, and they're very highly sought after. And what this shows is the number of AM Canvan stars known. The first one was obviously discovered around 1970. And a major big project, 10 times more cost than PTF, but doing 10 times more science came up, SDSS, and PTF is now continuing this exponential growth, and this is a project led by graduate student David Levitan. So why are they so interesting? Well, these are interesting because these white dwarfs are so close that they will generate detectable gravitational waves. And this is what it's an artist's conception, and you're supposed to view these outgoing waves as gravitational waves. So this is sort of one of the final frontiers of physics, which is, how does matter work under very high gravity, basically generation of gravitational waves. And so the LISA mission that one day hopefully will get done would surely see these gravitational wave signals from AM Canvan stars. Okay, so and I've given you a rather broad brush picture, which is only reasonable for a talk, which is constrained by an hour. And I hope I've given you an idea that, by and large, we understand many of the supernovae, but a project like this, even though it is modest on the scale by which astronomy is done, we're finding all sorts of new things and other things as well. And so we did start off with, let's go and look for weird things, and we have weird outcomes. So we, for example, the end product of that previous picture, we don't know. It could be carbon stars. It could be one of these calcium-rich supernova. You know, that's what you get this calcium from these. It could be thermonuclear explosions. So right now, we have some rough idea what these new findings are, but it's a very fertile time. As I said, it's very fun to be in a field where you discover something, and it's not the 1,001 thing. It's the second thing or the third thing, okay? And you always want to be in a field where it is a second or a third thing, because then it's easy. You can be pretty idiotic and still make great discoveries. And that's always been my philosophy, okay? Not the idiotic part, just to be doing easy stuff. Okay, so so we've done 1,500 supernovae, been there, done that. We could continue doing that. That's one way to do science. But last year we said, let's go and do something different at this point. And so the idea is to do everything in the same night. It's a technical challenge, because you have to observe the data, run these pipelines reliably, and then find something reliably, trigger another telescope, get a spectrum, all this sort of stuff. So we kaizened our way through it. This is a Japanese manufacturing philosophy, pioneered by Toyota, which is you understand the process and you find every little process where you can make a few percent change. Rather than finding the biggest term, you actually believe it's 5% here, 3% there, 1% there. So it took us a year to kaizen our way through and understand where we are making all these delays. And then we are finally with object where we're called about a year and a half ago, we were able to achieve same night action, which the technical term is low latency, which means do things the same night. And we're able to do this. And this goes to show you the slight complexity in this. So here's the data got recorded here. By the way, this is in days here. Okay, somewhere here it should be. Yeah, here's in days, 0 to 2 days. Got recorded here, right? And then Oracle, that is the machine language thing, figured out there's a supernova and it was in a nearby galaxy, enough to alert our team here in Israel, just take a look at it, because before you unleash all these major instruments, you don't want it to be a bad call. And so we're able to do that. And after that, look at all the stuff. There's Gemini, this is in South America, this is probably in Hawaii, this is in New Mexico, that's in space. So we're able to, because we are confident at this point, so we're able to now show that we went from discovery to action in the same night. And we are rewarded in a way that I thought it will never happen. This supernova 1A, the ones which have a lot of value, because these are the cosmic yardsticks by which astronomers have shown dark energy or inferred dark energy. We don't know what they are. It'll be useful to know what they are. I mean, they have served a good purpose. But there's been a huge amount of speculation what they could be. All we know is that giant thermonuclear explosions. They're carbon stars that one day decide they'll undergo exponential nuclear fusion, and then they go all the way to iron, okay? And the idea is there are several channels. There are two degenerates, like the one I showed you, where the two stars coalesce and it explodes. And the other one is it's a white dwarf, which is accreting matter from a companion and eventually becomes so massive that it then explodes. Anyway, so thanks to this fact, we could do everything in one night, and we are ready, and we are lucky. And as I said, it's more important to be lucky than to be bright, and so we're very lucky. And here's a PTF in the Pinwheel galaxy. This Pinwheel galaxy, we found a 1A supernova only 10 hours after it exploded. And this is the last such thing happened. I don't mean in time, but in distance. Such a nearby supernova happened was 25 years ago. And so obviously we are lucky, because we got this mode going, and a few months later we discovered something that happens once a quarter century. Okay, so somewhere here's a supernova, and actually I was giving a physics talk, so I asked, and there are a lot of string theorists, who are otherwise bright people, and I said, well, could someone tell me where's a supernova? And one of us smart string theorists says, yeah, it's easy. They come with arrows. Okay. And yeah, so that's a supernova, except as you all know, since you're not string theorists, the arrows are put by us after the fact, okay? Okay, so this already led us to 2 Nature papers with a single object. That's high efficiency, actually. So, it's sort of like scientists are like any other people. We have our own little way we count marbles and so on. So a Nature paper is like worth 10 marbles, whereas the one published in some other society journal is only 1 marble. So I'm always a big fan, least amount of work, maximum gain. So to get one object and 2 Nature papers, that's pretty good returns. Okay, so my wife is a biochemist. She always says, you get such cheap Nature papers because apparently in biochemistry you have to struggle for like 50 years and you get a Nature paper or something. Yeah, what can I say? We're just very smart people, Okay, so here is that sky picture. So what this shows is an astronomer, picture. This is basically the equatorial plane, North Pole, South Pole, and this is showing what part of the sky we are observing. And here's the date. And if you observed only once, it is this color. If you observed 100 times, it's that color. And black means we didn't observe. And this is not complete. I think I was unable to upload the final thing. We're actually filling up this quite well now. And by the time this project finishes, end of this year, we'd have a pretty good record of the northern sky. So we can really do amazingly new things that are nothing to supernovae. We can return and go to the glorious days of variable stars. We can investigate even things like dark matter and the halo by using special kinds of variable stars called RLI, and that's all happening. So one of the things before I conclude, I wanted to move on, wanted to make a point is there's a feeling that data are cheap, okay? There's lots of data out there. Well, that's true, there's lots of data. Therefore, there's a sense, it's all about the software or it's all about how you think. Well, that's also true. It's hard to deny any of these very large forces that are happening in a society. But if all of us just become data consumers, okay, I think the world will kind of run out of new creative energy. So one of the things that I'm very happy, and I hope we can continue doing this at Caltech, is actually provide technical training and opportunities for people to continue creating new things with their hands, with machinery, and so on. So I would say I'm very happy with each of these young people. I gave them right after their PhD or during their PhD, like Mansi here, huge opportunities. They actually got into the nuts and bolts of this project, and they're now capable of actually going and doing bigger and larger projects. At some point, someone has to actually build these systems, and everything doesn't come on Google by magic. It's something that many people don't understand, actually. Okay, so it's been fun. We operated PD for 3 years, and generally I like to actually have a sunset. Always, it's very important when you start a project to define an end point. Otherwise, if in academia, people want to continue doing the same thing till they retire or die or things of that sort. So end of this year, we are done. So that the idea is that it'll give us some new ideas what to do next, so they have some ideas for the next 2 years. But what about beyond that? So we're already starting on a new idea. So let me go back to my phase space. And this time I've shown you the same phase space, time scale on one axis, how bright they are on the other axis. And we only explored the sky from 1 day to maybe 100 days. Okay, actually there's a new bit of sky here more than 100 days, years, which we'll probably start thinking, and others are working on that. But what about below 1 day? Why stop at within the same night? Why not within the same hour? And maybe there are things there. Why not within the same 10 minutes? Why not within the same minute? I don't know. If I knew the answer to this, I wouldn't be doing astronomy because I'd have great perspective in the future. I'd be on Wall Street. But I don't know. And so there's a big question mark. So I would say the short time scale stuff below a day is technically hard because you got to get all these things running reliably and fault tolerant and very quick response, and they cost. Every factor of 2 reduction in the latency is exponentially harder. So anyway, we have already started planning the next generation facility, which is to go below 1 day. So we're going to image things at high speed now, or relatively what we're doing. which means if I'm looking at the same piece of sky many times a night, I'll explore fresh sky less. So we're going to increase the field of view. It's possible to populate the entire focal plane with CCDs. So we'll go from 8 square degrees to 40 square degrees. And we already, one of the young persons is leading a project to actually build is building a spectrograph that is on a robotic telescope. So it finds stuff, robotic telescope sleuths gets a spectrum. You know, all the stuff that where we are a bit in the loop is gone now. So the idea is the response time should be 10 minutes at this point. You want to get light curves, and that's the technical term is photometry. There's another project a young person is leading. And finally, you know, I worked for about 25 years on a NASA mission called Space Interferometry Mission, which is a great idea. Unfortunately, it got zeroed out in 2010. And then I said, you know, I have two options. Either I should maybe start taking Prozac or should do something more meaningful. So I said, okay, let me do something more meaningful. And so with a bunch of colleagues, I called them and I said, let's go and think something completely different. Everyone is building big satellites. Let's build small satellites. And it's called LIMSAT. And the idea is LIMSAT is less is more, is LIMSAT, okay? Because I'm tired of doing more is less or more is more. So anyway, so after about 18 months of, you know, the idea was not the astronomy, is yeah, whatever we'll do, because, you know, science is so interesting, you really have to be very narrow-minded to say this is not interesting. So the idea was, it's not so much what astronomy will do, it's like payload less than 100 kilograms, what is the best thing we can do? What's the easiest way to write those Nature papers? And so finally, after 18 months, we came up with this plan, and so I'm now working, the Israeli Space Agency is supporting us for half the cost, and I'm trying to busily convince these other nations to join. And I don't know whether you heard of something called the stone soup story in a Russian fable. That's exactly what the plan here is. So now I've convinced the other guys, I got half the stuff. If only they'd add a few tomatoes and potatoes, things would be great. Okay, so, and in honor of Zwicky, I thought it would be nice if we could name this as the Zwicky Transient Facility, not factory, because it's now an integrated approach. It is air and ground to go after this in a way of integrating as a major transient facility. So I'd like to end in the last 5 minutes on something slightly different, which is something I think a lot about. So I have to explain to you what I think a lot about. Actually, I spend maybe 3/4 of my time figuring out where things are going. Because in my opinion, and as Tom said, I sort of change fields. It's not because I want to change fields. I really find it very hard to work on the same thing after about 3 years. I just sometimes come to my office and throw everything away I've done because it's like I can have a fresh start. So, but if you want to be such personality, you have to figure out what's the right thing to do next. So I am a keen observer of the financial market because it's the greatest human laboratory of how people behave. And that's what I need to understand because this is a game. I know that it may shock some of the younger students. Oh, here's this professor. We thought we were doing all this for curiosity and the better endearment of mankind. So, well, okay, I think you should think that way. But for me, this is a game I want to win. And it's a game between you, me, and everyone else. So I think very hard of what problem to choose because that is far more important than anything else. It's very easy to get a solution for a well-posed problem, okay? Okay, so having said that introduction, I would say astronomy, and in my mind it's also true of biology, and many areas of science are actually undergoing a profound shift, okay? And this LIMSAT, I think, is an example of that, where less, well, first of all, less will have to become more because I think there's less money anyway. So the old idea of science in astronomy was like the pyramid, okay? Astronomers do little things with their little telescopes, then you find something, you go to the next big telescope, then you go to the next big telescope. The opportunities to observe become smaller and smaller as you go up. And finally, when you have that one great thing you want to do, you go to Keck or Hubble and get this one orbit or one night or something. So that's what I call as a pyramidal approach. Well, who can deny? Pyramid is a great architectural thing. We all love it and so on. Okay, the problem with this sort of approach is, as the ancient Egyptians themselves discovered, you can't keep building bigger and bigger pyramids. At some point, the thing collapses, actually. I don't think it'll be possible for us to just say, oh, well, we built Hubble, let's build James Webb, and then let's build James Webb plus plus, and so on and so forth. It'll actually collapse. It may collapse in a lot faster than most people are thinking. However, there are other changes that will offset this sort of what I consider as linear thinking. And one of the biggest changes that's happened in our lifetime is exponential growth. The world hasn't seen exponential growth historically, okay? And so we all know Moore's law, which is that there's an exponential growth in semiconductor industry, right? That's Moore's law. Well, I have a slight law, which I think, in fact, you can get beyond exponential returns if you can figure out those areas where the two technologies or two new things happening at the same time. That growth lasts for a very short time, but if you're a sharpshooter, you take advantage of that. And I consider myself to be an astronomical sharpshooter more than anything else. So the building I have in mind is not the pyramid. I have this in mind, okay? This is the opposite, okay? Less can be more, and thinking contrarian can be great. And I think this is a very beautiful building, actually. And so I want to go back to this, the thing. We took a 50-year-old observatory, and by repurposing it, refocusing, we were able to do extremely well. You know, we've been writing a paper every month, and in principle, we should be able to write a paper every 3 weeks, but it got so burdensome after writing, you know, what the 40th paper, I said, oh, I need a sabbatical from paper writing. Okay, so that goes to show that there are opportunities that are sideways, is what I call. And that's happening because it's very hard to think of such a facility even 10 years ago. It's the fact that there are all these exponential growth opportunities elsewhere that made a small project like this possible. But there are two lessons I learned. One is you really need to focus. You know, you can't just say, I want to do everything for everyone. Okay, and that's the old style. We build a large telescope, everyone is happy because they get their 1 night, 2 night here, and so on. Okay, but if you want to do any of these very high exponential growth things, you must focus very strongly. And second, which is very, very important, is these sorts of gains can only be realized if you have very smart people around you. Okay, either you can have a large telescope or smart people. They're more or less very unique opportunities. So I have all these young people. This is the next generation. I told them, come and work with me. I said the same formula. I'll make you, this time I told them I'll make them famous. And they're working away. So let me now end by saying, as we go to press, let's see, here's the Wall Street Journal, which I do read, along with my nature things, you know, because this is how, okay, here's 21st of April, page B1. A quixotic quest to mine asteroids, and it has all these very well-to-do people very interested in things. They want to now go and capture a small asteroid, bring it back, and so on. Well, I want to tell all our friends that we actually done this. The Keck Institute has, in fact, just submitted a report for asteroid retrieval feasibility study, and we, in fact, have proposed with PTF, we'll go find these very small objects which are streaking because they're moving so fast, they're so nearby, that they, in fact, even in 60 seconds, they will streak across the detector. And then, because we have set up this very fast response things, we'll, in fact, compute where they will be, get a spectrum, we'll say what kind of asteroid it is by looking at the spectrum, we can say something, and just try it out. This will be the thesis topic of one of the grad students. Of course, you know, this is very timely, but really what I want to do, this will take some time because the project that has been costed out by NASA is about $2.5 billion, and who knows how long that'll take. And as I told you, 10 years is to me it's beyond lifetime for me that I can't wait. What I really want to do is I want to find those asteroids which will, you know, it shouldn't be big, it shouldn't be too big because I want to live and all that stuff, but, you know, but enough that we can recover stuff. And there's an example. So here's a survey, and I like this survey because they too have a single focus. It's called Catalina Sky Survey. It uses only small telescopes, and they haven't done all this sort of automation, machine learning like we have done for asteroids. But nonetheless, they did notice one of these asteroids was moving. They called up JPL, and the group that computed, they said it'll intersect Earth in 14 hours. all assets, both known and unknown assets, focused on the entry point in the northern Sudan. And in fact, the asteroid broke up. 200 pieces were collected by a professor from the University of Khartoum with his students. And so my plan is, I like this because I want to use PTF in the next couple of years, find these re-entry things, collect those things, sell them on eBay, and fund myself. Anyway, so let me leave with this picture. The future doesn't have to be like what you're thinking. Bigger is not always better. More can be more, but more can many times be less. Building like this is both inverted, it's exciting, and there are many opportunities here to do things. Thanks.